So good afternoon. All. So this week's tutorial is actually, the solutions like always, it is already uploaded on Moodle, right? So there's three sets of problems that has been given actually. So let's go over them. Problem number one: assume a 1 ampere hour battery that is used on a cellular phone. Assume that the cellular phone draws 35 milliamps in idle mode and 250 milliamps during a call. How long would the phone work? One, if the user leaves the phone always continually powered on and has 1 3-minute call every day. So basically in a whole day, what happens is that the user just takes a 3-minute call. Otherwise the phone is left on idle. So in a day, right, if you go to the solution, so in a day, there's 1440 minutes. So basically that is 60 minutes multiplied by 24 hours, right? So in a day we have 1440 minutes. So out of 1440 minutes, what happens is the user just takes a 3-minute call in that particular day. So we have to find out how long would the phone work. So the average current drawn is basically so a 3-minute call that will cost him, that will cost him or will use up 250 milliamp of power, right? So 3 times 250 milliamps plus the remaining minutes in from that particular day. So that is basically 1440 minutes minus 3 minutes. The remaining time, the phone is on idle mode. So in idle mode, the battery consumption is basically 35 milliamps. So basically averaging that, so this is the finding the average current drawn in that whole day. So using this particular representations, so we get the average current drawn or required is that is 35.44 35.448 milliamps, right? So the average current that is required to be drawn when a user takes a 3-minute call in that whole day, while the phone is left idle for the remaining minutes, is 35.448 milliamps, right? So if the battery can supply 1 amp current for 1 hour, then it can provide X hours of 35.448 milliamp current, right? So what we do is we need to find the X number of hours of operation. So in this particular case, we know that 1 ampere current for 1 hour is being supplied by the battery. So we need 35.448 milliamps. Or basically on average, the the user requires 35.448 milliamp of current in order to conduct this particular activity over here, right? So what we do is we divide 1 ampere by 35.448 milliamp to get the total number of hours of operation. So in this particular case, if we do that 1 ampere divided by 35.448 milliamp, we get X number of hours of operation. So that will be equivalent to 28.21 hours, right? That is basically equivalent to 1 day, 4 hours and 1 day, 4 hours and 12 minutes, right? Then moving on to part 2 of this particular question. Again, if the user leaves the phone always continually powered on and has 1 3-minute call every 6 hours. So if a user takes 3-minute call every 6 hours, so we have 24 hours in a whole day. So basically there will be 4 sets of 6 hours, right? And every 6 hours there will be 3-minute call. So basically after every 6 hours we'll be having the user will be taking 3 minutes call. So in a 24-hour period, the user will be taking 4 calls of 3-minute long, right? So that will be 4 multiplied by 3. That means the user will be taking a total of 12-minute call altogether in that whole day, isn't it? Right? So so in that particular case, what happens is the user will be basically taking a 3-minute call every 6 hours. That means a total of 12-minute call in a whole day, right? 12-minute call in the whole day. while the remaining minutes, the phone will be left idle. So again, finding the average current drawn by this particular user's usage is equivalent to finding the average. I mean, writing the average current equation for this particular case is 12-minute call, right? So that is 12 by 250 milliamps, since the phone consumes 250 milliamps per call. I mean, like 250 milliamps per minute per call, right? So we basically multiply 12 minutes by 250 milliamps plus the remaining hours or remaining minutes in that particular day is idle. So in that particular case, that will be 1440 minus 12, right? This is the remaining time. That is, this is the time for the phone to be left idle. So 1440 minus 12, right? Multiplied by 35 milliamps, because the phone consumes 35 milliamps when it is idle, right? So multiply by 35 milliamps, and then since we are averaging the current, so we divide by the total minutes or total minutes in that particular day. So divide by 1440 minutes, or the total. We can also say that the total minutes of operation for, I mean, like total minutes of operation for the call plus the total minutes of operation for the phone to be idle, right? So the total time, or divide by the total time in this particular case, will give the average current needed for this particular user's requirement, right? So in this particular case, if you do the average of it, right? So this is the equation that we get. So finding the average, we'll get 36.79 milliamps, right? Again, the user needs an average of 36.79 milliamps, and we have a 1 milliamp hour battery. So what happens is, if we divide 1 milliamp hour, right, 1 milliamp hour by this particular current, we get the x hours of operation. So again, one ampere, the 1 ampere hour divided by 36.79 milliamps is going to give us is basically going to give us, again, 1 divided by 36.79, right, is going to give us 27.18 hours, right? So this is the this is in hours. So in converting this into days and hours and minutes is going to be equivalent to 1 day, 3 hours and 10 minutes. Okay. Moving on to part 3 of this particular question. Again, it is the same thing, but now, I mean, like, it's just broken down. Like, there's different requirements for the core part, right? So moving on to part 3, if the user leaves the phone always continually powered on, right? So basically, the user leaves his phone on idle mode always, and has 1 3-minute call every hour. So if the user takes 3-minute call every hour, so he'll be taking 24 calls in the 24-hour period, isn't it? So 24 multiplied by 3 minutes, so that will be equivalent to 72 minutes of call altogether, right? So in a whole day, for 72 hours, so for 72 minutes, the user will be taking the call, right? So each call consumes 200, I mean, there's a 250 milliampere consumed when during a call, right? So again, finding the average current required for this particular use, it is basically given by 72 minutes multiplied by 250 milliamps, right? So 72 minutes is the total call time multiplied by 250 milliamps. That is the amount of current needed for each call, right? Plus the remaining minutes in that particular day. So that will be 1440 minus 72 into 35 milliamps. 35 is the idle time, right? The current required for putting the phone in idle mode, right? And then divide by 1440 to find the average current. So the average current will be basically 45.75 milliamps required for this particular use case in 3, right? So again, finding the X number of hours. So basically 1 ampere hour divided by 45.75 milliamps will be getting the number of hours of operation that can be delivered by that particular battery. So that is, in this particular case, is going to give us 21.85 hours. And that equates to basically 21 hours and 51 minutes. Then part 4 of this particular question, what is the maximum talk time? So the maximum talk time is basically equivalent to, so basically we just need to find the maximum talk time. When we mean by, what do we mean by talk time is basically calls, right? The number of minutes or hours of call we can obtain from this particular battery. So a call basically consumes 250 milliampere, and the battery can supply 1 ampere per hour. The 1 ampere hour, I mean, that's the capacity of the battery, 1 ampere hour. So what we do in order to find the number of time, we divide this particular power, 1 ampere hour, divide by 250 milliamps. That will give us the total number of hours of talk time. So in this particular case, we have 1 ampere hour divided by 250 milliamps, right? So that could be written as 0.250. So basically that is equivalent to 1 upon 0.250, which is equal to 4 hours. So yeah, so that's regarding part 1 of this, I mean, problem number 1 of this particular tutorial. So do you have any questions regarding this?
No, sir, it's all right.
So this is pretty much simple, right? This is, I think, a recap of PH301 work, isn't it?
Yes.
Yeah. So moving on to problem number 2, again, a base station. Problem number 2 says a base station radiates at a transmitter power of 50 watts. Let the carrier frequency FC be 900 megahertz. Let D naught be 100 meters. Assume the free space path loss model between the transmitter and D naught, right? So D naught is basically a distance at a particular point D, right? Or D naught is the point basically 100 meters away from the transmitter station. So assume free space path loss model between transmitter and D naught, right? So basically we have the transmitter, right? Let's say, I'll just write this as D. And then at 100 meters away, we have a point D naught, right? So anything within, and then there is something, and the receiver is somewhere here, R, right? So receiver is at some distance X. So 100 meters away is the point D naught, right? So this is 100 meters away. So anything that assume free space path loss model between transmitter and D naught. So anything, any distance between these two, I mean, between the transmitter and D naught, any distance between this is going to basically incur a free space path loss, right? So any we'll have to consider the free space path loss model between I mean, for any distance between the transmitter and the distance D naught, right? And then it says, and log normal shadowing loss model for distance greater than D naught. Assume path loss exponent. No? I mean, sorry, yeah. So we basically need to any distance greater than this D naught. So anything greater than this. So basically any distance greater than 100 meters, we have to assume the log normal shadowing loss model, right? So basically that's the loss that will occur when the distance exceeds 100 meters, right? Then it says assume the path loss exponent n of 3 and sigma of 5 dB for log normal shadowing model, right? Find out one, the received power in dBm at 100 meters. So basically we need to find the receiver power or the received power at 100 meters. So basically what happens is that let's assume the receiver is at D naught, right? So like it said, anything between the transmitter or any distance between the transmitter and D naught, we have to basically assume the free space path loss model, right? So using this particular model, we can find our receiver power because we have our transmitter power, we know our frequency, and we know our distance. So the free path loss model formula is basically PR upon PT, right? The receiver power divided by the PR divided by PT, or the transmitter power, is basically equivalent to the gain in transmitter multiplied by the gain in receiver multiplied by lambda squared, whole thing divided by 4 pi d squared, right? Since this, I mean, like you can see this solution is quite messed up. I'll use this solution over here. This one is quite properly written, right? It is somewhat similar to our, I mean, it is similar to our problem, but only thing is that part 4 is not part of our tutorial here. So yeah, so I'll just basically use this particular solution to explain our solution over here. It is the same thing. Only thing is that you can see when we have lambda squared, this 2 is actually brought down, right? So to avoid that, I'm going to use this, right? So the free space path loss model actually is given by PR upon PT is equal to GT times GR times lambda squared divided by 4 pi d squared, right? So rearranging the equations, right? So this is the equation you get for the free path loss, where the PR is equal to, or the transmitter power is basically equal to, the receiver power is basically equivalent to the receiver power, the transmitter power multiplied by the transmitter gain multiplied by the receiver gain multiplied by lambda square divided by 4 pi times d squared, right? So in this particular case, since the gain of the transmitters are not given, so we'll assume that the transmitter and the receiver is not given. So we'll assume GT and GR to be equivalent to 1, right? So in that particular case, since our transmitter power is 50 watts, so 50 times lambda. So the lambda value can be basically found from, lambda is basically equivalent to speed of light divided by frequency, isn't it? So in this particular case, it is going to be speed of light is basically equivalent to 3 times 10 to the power of 8 meters per second, divided by the frequency is 900 megahertz. So doing that, you'll get lambda is equivalent to 0.33. So in that particular case, lambda is equivalent to 0.33. So substituting that value into this particular equation. So the transmitter power is 50. The gains of the transmitter and receiver antennas are 1. So we can ignore that, right? We can ignore GT and GR. So we just need to directly multiply by lambda squared. So lambda value is basically given by this. So the lambda value is 0.33. So square of that, right? Take the square of that. Divide by 4 pi will remain as it is, multiplied by the distance, right? Distance squared. So in that particular case, the distance is 100, right? In our case is 100. So distance is 100, so 100 squared. So that will give us the receiver power equivalent to 3.45 times 10 to the power of -6 watts, right? So we have to basically find the power in dBm, right? So what we do is we take the milliwatt of these, right? So 3.45 times 10 to the power of -6 watts converted into milliwatts is going to be equivalent to 0.00345 milliwatt, right? So basically we have to take 10 log of this particular value over here, right? So that would be basically, 10 log of the milliwatt of this particular value, right? So converting this into milliwatt is going to be equivalent to 3.45 times 10 to the power -3 milliwatt. So converting this wattage into milliwatt is going to give us this value. So we basically have to take we just basically have to take 10 log of this particular value. So that is going to give us in dBm. So that is basically equivalent to -24.62 dBm, right? So converting this into dBm is going to be equivalent to minus 24.62 dBm. So that is the receiver power for this particular, when the receiver is at a distance of 100 meters, right? Next is find the mean path loss in dBm from the transmitter at 500 meters. So like I showed you over here, right? Actually, I think I erased it. Sorry. Oh, sorry, I'm using this version. Yeah, like I showed you over here. So anything, since this, the mean path, we have to find the mean path loss in dB from the transmitter at 500 meters. So what happens is the 500 distance is somewhere over here that is beyond this distance d0. So the first 100 meters is going to experience, right, the first 100 meters of this 500 meters, right? So the total distance is 500 meters. So this is 100. So the first 100 meters is going to be equivalent to our, is going to basically be the, be basically denoted by the free space path loss model, right? And then anything beyond this d0 point, that is the remaining 400 meters, right? So the remaining 400 meters is going to be modeled by the log normal shadowing loss model, right? So again, the mean the mean path loss, right? The mean path loss in dB is basically equivalent to mean path loss d0, right? Or basically the mean path loss between the transmitter and the point d0, right? Plus 10n log d upon d0. So this 10 n log d upon d0. This is your, this is what do you say? This is your sorry, yeah. This is your log shadowing model, right? So log normal shadowing model. So this is going to give you the log normal shadowing model loss, right? This particular value, and this particular value is going to be denoted by the free space loss model, right? So finding that, so the mean path loss at 500 meters is in dB is basically equivalent to so that is going to be 10 log into 50 watts divided by 3.45 times 10 to the power of minus 6 watts. So remember, the free space loss model is basically given by the receiver power divided by the transmitter power. So that is why we are going to use 10 log. So this is basically converting the ratio PR upon PT into the dB value. So 10 log of 50 watts. This is your receiver. This is your this is your transmitter power divided by the receiver power over here, right? So let me just show you the free space loss model formula. Okay, path loss formula, because I cannot write it over here, so that it becomes clearer. Okay, the free space loss, the free space path loss, right? Excuse me, it was supposed to be PR. It was supposed to be PT upon PR, right? I said it wrongly before. So the free space loss, the free space path loss, or FSPL, is basically equivalent to PT divided by PR, right? So in that particular case, converting this particular value, PT upon PR, into dB is going to be basically 10 log of PT divided by PR. So the path loss, the mean path loss for 500 meters, right, at a distance of when the transmitter, the mean path loss in dB from the transmitter at 500 meters is basically given by the free space loss model, right? So that is basically given by 10 log of transmitter power divided by the receiver power, right? Plus the log normal shadowing model, right? So the log normal shadowing model is basically given by 10 times n times log of d upon d0. So in this particular case, it will be plus 10. Our n value is given over here, that is 3. So 10 times 3 times log of the distance given is 500 meters. So 500 divided by d0. So d0 is d0 value is given as 100 meters. So 500 divided by 100. So evaluating these particular values, it is going to give us, and this term over here is going to give us the value of 71.61 dB plus this particular value over here, that is going to give us 20.96 dB. And adding these two up together, right, these two values over here, that is going to be equivalent to 92.57 dB. So the mean path loss in dB for the transmitter at 500 meters is going to be equivalent to 92.57 dB. Okay. So that's regarding part 2 of this question. Moving on to part 3 of this question, it says the mean, we have to find the mean received power in dB at 500 meters. So the mean received power at 500 meters is basically going to be equivalent to the mean received power is going to be basically equivalent to the transmitter power, the dBm value, right? In how can I explain this? So what we can do is based on this, right? The mean received power, right? The mean received power is basically equivalent to PT, right? Transmitter power in dBm minus the mean path loss at 500 dB, right? So that is basically going to be equivalent to 10 log of 50 divided by 0.001. So this is basically converting 50 watts into milliwatts, right? So 50 watts into milliwatts is basically equivalent to, or basically finding the dBm value of this particular 50 watts. So in order to find the dBm value of this 50 watts is basically first convert this into milliwatts. So that will be equivalent to 50 times 10 to the power of 3. So that will be 50,000 milliwatts, right? And then finding the 10 log of that particular value is going to be equivalent to 46.98, right? So this particular value is going to be equivalent to 46.98, right? Or 46.99. And then this particular value, the mean path loss value has been already calculated over here, that is 92.57. So subtracting 92.57 from this is going to be equivalent to, so this particular value is 46.98 minus 92.57 dB, that is going to give us minus 45.58 dBm. Why aren't we converting this particular value into dB? It is because you can see that the mean path loss formula over here, the mean path loss formula is a ratio of two particular variables, isn't it? So even if you convert this 50 watts into milliwatts and this particular value into milliwatts, the ratio over here, the 10 log of this particular ratio will not change. Similarly, for this over here, d upon d naught, the ratio, regardless of whether you convert it into dB or dBm, the ratio does not change, right? It is same. So that is why we do not need to, I mean, like, even if you change this watts into milliwatts and this watt value into milliwatt, it is going to be, the value will remain same as it is. So that is why we do not change this particular value into dBm, right? Because the value that you have calculated is basically the dB value of the ratios. So that is why we do not change this particular value into dBm. How we get this particular formula over here, you can see from this particular path loss formula, the loss is basically denoted by the transmitter power divided by the receiver power. Okay, so the path loss is basically equivalent to the transmitter power divided by the receiver power. So if it convert this into log, right? If you convert this particular value into log values, what happens is this particular value is actually, I mean, if you convert this into log, so what happens is you'll get this into dB, right? So the PL value into dB is equivalent to the transmitter power in dB minus the receiver power in dB, right? So once you have that particular value, what happens is if you take this PR to the other side, that will be PT is basically equivalent to, oh, sorry, we have to find PR, right? Isn't it? So what happens is if you take the PT to the other side, sorry, if you interchange, if you take this PR to that side and if you bring the PL down over here, we'll be basically having PR is equal to PT divided by the path loss, right? Isn't it? So now converting this into log value, it is going to be, this PR will be into log into dB value, right? So basically taking the 10 log of this particular value is going to be equivalent to 10 log of PT minus the dB value of this path loss. So this is where we get the get this particular derivation from, right? So this is what is being represented by this formula over here. But the only thing difference is that this is into dB, but this is as it is in terms of value. So that is regarding this particular question. So you have any questions regarding this?
No, sir. All good.
Everything must be flying over your head, isn't it? Okay, anyways, let's move on to part 3 or problem number 3 of this particular question, this particular week's tutorial. Problem number 3 says consider a communication system operating in 5.9 gigahertz, or that is basically represented by 5.9 gigahertz band, right? So this is in words and this particular value is given in numbers. Assuming the free space loss model for signal attenuation, the gain of both the transmitting and the receiving antenna to be 1 decibel, right, 1 dB, and a noise level of minus 85 decibels. Calculate the range of the communication in transmission power. The transmission power. Oh wait, it says calculate the range of communication if the transmission power is 100 milliwatts, right? So we have to basically calculate the transmission power. So again, using the free space loss model, that is basically represented by PR upon PT is equal to GT times GR times lambda squared divided by 4 pi T whole thing squared. So from this, we know that our receiving power, oh sorry, yeah, from this we know that our transmitter power is basically 100 milliwatts, right? So that is given over here. We have to find the range. So we basically what we'll be finding in this particular formula is the D value. So we know our transmitter power that is equal to 100 milliwatts. What else do we know? We know our receiving power that is given over here, right? So our receiving power is basically minus 85 dBm. So basically what we can do is, since our receiver power is in dBm, so we can basically convert this transmitter power into dBm as well. So taking 10 log of this particular value is going to give us is basically going to give us 20, right? So the value will be 20. So yeah, so 20 dBm. So transmitter power is basically equivalent to 20 dBm, and then the receiver power is basically given by minus 85 dBm. Now, what else do we need to gain the transmitter and the receiver gain is given by 1 dB, right? So we do not have to worry about the transmitter and receiver gain in that particular case. What else? We need to find our lambda, right? So from this particular formula, we also need to find our lambda. So lambda is basically given by C divided by F. So C is a speed of light. So we dividing that by the frequency. So in this particular case, the frequency is 5.9 gigahertz. So basically, lambda is equal to 3 times 10 to the power of 8 divided by 5.9 times 10 to the power of 9 is going to give us 0.051. So our lambda is basically equivalent to 0.051 meters, right? Now converting this formula using the logarithmic rules, this whole formula will simplify down to PR in dBm, right? So all the values will be in dBm. Remember, if it take 10 log on both the sides and use the logarithmic properties, try to simplify this, we'll get this particular formula, right? So PR in dBm minus PT in dBm is going to be equivalent to GT, right? GT in dBm or dB multiplied by GR in dB multiplied by 20 log of lambda, right? 20 log of lambda minus, right? 20 log of lambda minus 20 log of 4 pi, right? So minus 20 log 4 minus 20 log pi minus 20 log d. So then what we have to do is take these particular values and plug it into this particular formula. Why we are taking dBm on one side and why we are taking dBm on the other? Because the values over here, what happens is this is a ratio, right? PR upon PT is a ratio. So regardless whether these powers are in milliwatts or watts, it does not matter. So converting this into dB or dBm, this will remain as a ratio, right? PR in dB, right? It will remain in terms of in a ratio, right? So what happens is that extra values that if you use to convert this into dB, that plus and minus 30 will be cancelled off in this particular case. So that is why we let PR and PT remain as it is in dBm values, while the other sides have to be in dB. So expanding this into log using the logarithmic formula, we get this something like this. And substituting our values for GT and GR. So substituting the values of a GT and GR, that is 1 dB each. So 1 plus 1 plus 20 times 10 log lambda. So lambda value is basically 0.051 minus 20 log of 4, right? This 10 is basically the base, right? The logarithmic base in this particular case. So minus 20 log 4 minus 20 log pi minus 20 log d. And making d the subject of the formula and solving for the whole equation, we get d is equivalent to 908 meters, right? Part 2 of this particular question, the transmission power, if you want the communication range of 3 kilometers. So basically in this particular case, what happens is the formula will remain same again. What changes is the distance is now, the distance is given to us, right? So the d value is given to us. However, the transmission power is not given. So the formula will remain as it is, right? As it is. However, in place of d, we'll plug 3 kilometers or basically 3,000 meters, right? Remember, when you are using this particular formula, it will be in SI units. So in place of d, we plug in 3,000 kilometers. So 3,000 kilometers in place of d. And in this particular case, our transmission power will be unknown, right? So solving for PT, right? Solving for PT will be basically getting our value as equivalent to, we'll be basically getting 29, I think, so we'll be basically getting 30 dB as our transmission power, which is basically going to be equivalent to, PT is going to be basically equivalent to 1 watt. Part 3 of this particular question says, what would the range of communication be if the frequency was equal to 900 megahertz? So in this particular case, we have to find the range again. Range is equal to the distance value. So what happens is we'll be using the same particular values over here, right? The same whole formula will be as it is. However, we'll be solving for d now, but our lambda value over here, the lambda value will change. So in that particular case, our lambda value is going to be c divided by f. So c divided by speed of light divided by 900 megahertz. So that is going to give us a lambda value of 0.33. So into the same formula, keeping our PR and PT value as it is, right? That is basically 20 dBm and minus 85 dBm. And in place of lambda, we have to substitute 0.33. Our d will be, the d value will be unknown. So solving for d is basically going to give us 5,932 meters, right? So that is the approximate values that you'll be getting, right? So do you have any questions?
No, it's just number A.